Good afternoon. Thanks for the introduction. It's a bit too much. So I'll try to convince you, and by all means, you'll see at the end that I don't have all the answers, that there is a future for terahertz wireless communication, and it can have an impact on future wireless systems. Fairly busy slide. There's a lot of issues with wireless at the moment. There's more and more demand, and we are requiring more and more data to go through wireless. And that goes from backhaul to the customer, or if you want to look as well at data centers. People are exploring a lot of solutions. Somebody came to me earlier in the demonstration and spoke about Li-Fi, so using light to transmit. In the radio system, people are trying to use massive networks of MIMO. So massive MIMO, they are trying to put smaller cells as well, so more and more antennas to try to drive more power. And that's one issue we're going to come back to. And another solution, that's kind of what I'm working on, and the purpose of that talk, is to try to look at higher frequencies that are between optics and radio, which is the terahertz range, which has its challenges because there are not many sources and receiver in that range. So why do we want to go there? That doesn't work very well, That's why you shouldn't do animations. That's a good lesson. We want bandwidth. That's a given. And we want more than 10 gigahertz bandwidth because that's kind of where the limit for radio is at the moment, so we want to do better. So I would say that we probably want carrier that are above 100 gigahertz where that bandwidth exists. And that's 100 gigahertz to optics. Ideally, because that's the most efficient, I spoke about energy, the most efficient in terms of energy per bits at the moment is fiber. Fiber doesn't work very well wirelessly, but if I could get the fiber as close as possible to my wireless channel, that's good news. So I'd like to be able to integrate seamlessly as possible with my fiber network. So that's kind of starting to limit me because the bandwidth of each of those optical channels is quite wide, and they are high data rate. I'm likely to be limited to optical wireless or millimeter wave or terahertz. So then those massive MIMO radio solutions, they are unlikely to work. And the last one, and that's why I had that little thing, is if any of you have ever tried to align a laser over long distances, you'll see how much fun that is. It's quite hard because basically alignment is related to wavelengths, and the shorter the wavelength is, the harder it is to align. So actually, we are better off at lower frequencies if we want to have ease of alignment. And that's where I think terahertz hit the sweet spot. We are 3 orders of magnitudes lower in terms of frequencies than optical. So we are 1,000 times it's 1,000 times easier to align. And we still have hundreds of gigahertz of bandwidth available, which means that we still have quite a large amount of bandwidth to which we can work with. Will I replace a fiber link with terabits, or actually petabits these days, of transmission? No. But I could probably reach terabits per second. And interestingly enough, I thought I put that one up because when I started to work in terahertz, it was 2002. And we have some publication around those areas. There were not many people working in that area at that point. There were basically 5 groups in the world. Since then, it's exploded a bit, and I can tell you that publication, although I couldn't drag the publication from Google, somehow it didn't give me a curve like this, are going the same way. And the number of groups working on terahertz communications is going the exact same way. And that's a sign that is becoming quite a subject across the field, and there's more and more interest into it. So let's see why we are going there. So as I said, my point is that this is still a very interesting area to go in, and there is potential for it, because we can get quite low complexity and large bandwidth. Of course, there's a problem of the source and the receiver that I mentioned before, because the problem you have with terahertz is that it's at a frequency where it gets hard to move electrons around. So electronic source starts to struggle. And for optical sources where you use 2 levels of energy, the levels of energy are not separated enough to be separated so that you can get a laser, for example, because you are limited by thermal movement. But in terms of transmission, I can look at quite a bit of bandwidth. So this is showing you up to 1 terahertz. I have another one that goes above. I give you free space path loss to give you an idea of how much losses I have just by the beam dispersing across. And then the absorptions, because you can hear a lot of people saying that there's a lot of water absorptions and everything for terahertz. Well, actually, is that the laser? Is that the laser on this? This top button. Yeah. There are a lot of bands that actually are not too bad depending on which distance you want to go. For even up to 1 kilometer, that band that has 120 gigahertz of bandwidth is fine. All I need to do is put a nice antenna to make sure that my beam doesn't diverge too much to compensate for the free space pass loss. And if you had a look at the demo, I know it didn't work today. We worked hard on it. It didn't work today. This is working at 300 gigahertz, and with relatively small antenna, we are able to do about 10 meters. If we put a bigger antenna, that's quite easy to go 1 kilometer. And at the moment, I say that, but there is a lot of discussion about making them allocated. It's unallocated, but it's going to change very quickly. So there's quite a lot of things we can do in those bands. And I can go further. I can go above 2 terahertz, and you could see that there are still some usable bands. That one in particular, here and here, they are still usable. And you have more than 450 gigahertz of bandwidth still available. You have more of a problem because you are at higher frequencies. But there you probably want to use something like a QCL, quantum cascade lasers, that work at 2 to 5 terahertz. But what you will lose from the other system is the integration with the optical network. So yes, terahertz is interesting. There's quite a bit of bandwidth, and water absorption is not as big a problem as people think. And actually, if I think about water, let's look about fog and rain. And you'll see that compared to optics, in particular for fogs, terahertz is better, quite a bit better, actually. While rain is fairly similar. So again, another advantage for using this kind of system for wireless. So we could do a little calculations, a little exercise. So typical source from the transmitter, that's the same source we have over there in the demo. It's about 10 microwatt at 300 gigahertz. It's quite typical. We can drive them a bit harder, but that would operate for days at 10 microwatt. Antenna gain, if I want to get some distance, 45 dBi. That's giving me the direction, how much directivity. So 45 dBi is quite high. So it's a comparison to emitting everywhere. And carrier frequency 300 gigahertz. The sensitivity of a typical receiver, minus 56 dBm, is quite classic. The receiver we have over there is actually a bit more sensitive. And the bandwidth, we are looking at we are thinking about tens of gigabits per second. So we are looking at 12.5 gigahertz of bandwidth. If I use 16 QAM, for example, that's going to give me 50 gigabits per second. That's pretty good. And we do classical calculations using Friis equations. And we can find that actually, yes, that works. I have minus 53 dBm at the receiver. I am 3 dB above my receiver sensitivity for 16 QAM. It does work. And I can do 100 meters, 50 gigabits per second. And the size of an antenna is about 57 centimeters in that case. So a bit bigger than what you saw over there, which was quite a bit smaller. So what can we do with terahertz? So as I said, there are a lot of solutions up there that I show up. You can use photodiodes, photoconductors, QCLs for the higher frequencies, the receiver transistors as well. So there's quite a lot of solutions that are now commercial using CMOS, silicon germanium CMOS, HAMTs. And most of the receiver at the moment are Schottky barrier diodes. There are other solutions, but commercially you will look at Schottky barrier diodes. There are a few things that are coming in, like phase arrays, amplifications, and antennas for steering and beam shape. Where do I go for this? So these are some examples of links that you can think of. At the heart of it is the fiber network. You could go to a kiosk for a quick download to a device, device to device for terahertz, very short links. No problem, that's quite short. Indoor, we are looking at nomadic, not mobile, because this is quite a directional beam. And following a customer, like a mobile customer, is probably too hard at the moment to follow. But small movement is possible. Backhaul, because there is enough signal. And vehicle to vehicle. So there's a lot of work, a lot of projects around autonomous vehicles as well. And this can integrate with the 5G or 6G network and the fiber network directly. So people have achieved actually up to 400 gigabits per second at hundreds of gigahertz of carriers, short transmission, and 1 kilometer with 10 gigabits per second. There are better results coming up now, and people have used electronics as well, 64 gigabits. There's been a 240 gigabits demonstration as well recently, and that's around the 300 gigahertz barrier, and that's almost a kilometer. Interestingly enough, there's a lot of solutions now that are popping up because there are more groups working in the area. People are looking at, for example, as reconfigurable mirrors or reconfigurable antenna transmission system on walls to be able to direct the signals. Think about those nomadic solutions. Phase array for mobility using leaky wave, for example, has been very interesting. There's been a nice demonstration from the University of Duisburg where they had 5 different clients in a shopping center and directed the terahertz beam to each of those clients. They were not very mobile. These were computers on a desk, but they were able to switch between each of the clients. So it's slowly getting to the systems that could be installed. So what does it look like? It's fairly simple. Classic link, transmitter. The transmitter typically is an electronic oscillator, either a GUN or a resonant tunneling diodes, photomixers, quantum cascade lasers. We can modulate them directly or transfer from optical fiber signal. That's a lot of things that we do at UCL. We come from an optical fiber and we just transfer it to the terahertz. And you could have polarization multiplexing, amplifications. There are a lot of things you can do. You can have multiple signals. You can do wavelength multiplexing and spatial multiplexing as well. Receivers are mostly Schottky biodiodes, but you could find photoconductive antennas and RTDs. There is a nice group in Japan looking at RTDs receivers. Often you need a local oscillator for that receiver because you want to down convert to lower frequencies for the electronics. And you might want a few other things like doing an optical bridge that remodulate onto an optical signal. You need a laser local oscillators and some amplification. So it's quite a lot of things. So these are some examples. Now I go to some examples that we have developed at UCL. And one of the things we are looking at is to do a wireless bridge. You remember I said I'd like to be integrated with optical fibers. So ideally, I'd like to have basically an optical fiber system, plug my terahertz transmitter to the optical fiber at one end, and plug my terahertz transmitter at the other end, and actually make it duplex. So those systems will have an optical central office. At the transmitter, I will have a secondary laser to do photomixing. And we are using photodetectors we have developed at UCL. And at the receiver, I use a mixer that will then modulate another laser to then send to my receiver, which could be coherent or direct detection, which means that suddenly I have a wireless link between 2 units. This is an example that we got from Dell EMC where we installed one of those systems. There are several ways you can do the remodulation. The easiest way would be to directly modulate, but there are not many modulators that are ultra-wideband enough to remodulate directly an optical system. So most often we do terahertz to optical conversion. Within my team, we have done the top 2. The next example is the second 2, where we have a mixer, a local oscillator, and we drive an optical modulator. And we filter out some of the signals. And that's what we managed to do. So that link was up to 10 meters long. We had 4 channels, all with 16 QAM, and 12.5 gigabaud. And as you can see, all of them were meeting the HD FEC limit. And it was possible to transmit across those 10 meters with all that system. I make a point here that this was all locked on a comb, which makes it a bit more coherent than if I had free-running lasers. And it offers some advantages in terms of your detection. So you get slightly better detection. So that worked quite well. So we wanted to extend this. We wanted to have now a receiver that was optically driven. Because if I have a terahertz LO, like an electronic source, they are quite power hungry. They need amplifiers. If I'm able to drive from one of my optical source, they need a few hundreds of milliwatts, max. But also they can tune from 1 gigahertz to 10 terahertz. So I can tune my receiver over a very wide range, which in a network where I have multiple channels, like this, means that at the receiver, I can switch and decide which channel I'm looking at. So I can do addressing through frequencies and receiving through frequencies. And such a system can be built. So we are looking at switch wireless here. So we designed, perfect. So I'm going to go a bit faster. I'm going to pass that. So we designed, integrated in a chip, such a receiver that has our photodiode developed at UCL, integrated with a Schottky barrier diode, a low barrier Schottky barrier diode, built by Rutherford Appleton. Oh, that did go very wrong. I'm sorry. This looked better on the original version. That's interesting. The losses are okay. And it's a state-of-the-art receiver that's driven photonically. That particular receiver can work from frequency, in that case, between 220 and 350, but actually it's only limited by the waveguides, the coplanar waveguide that we have designed. You can change that design, and the receiver will work at different frequencies. And with such a, well, all the images have gone wrong. Okay. We have done a 300 gigahertz transmission with this. The barriers are driven at 150 gigahertz by our photodiodes. And we have detected all the channels independently. And as you can see, we have reached data rates at the HDFEC well above about 80 gigabits per second, and at SDFEC well above 100 gigabits per second with those channels. This is single channel data. So if you have multiple channels, so we are at about 80, I think, from memory. Yes, about 80, and we had up to 4 channels. So we are we are at 320 gigabits per second total throughput with those systems. And there is very little penalty in that multiple channels. You can see that the differences are pretty small. Now I finish. We managed to put all of this on a chip, on a single chip. 2 UTCs, one as a receiver, one as a transmitter. This is a chip that's driven, and it combined power consumption of that chip's 200 milliwatts. I'm going to pass all of this because I don't have much time. Just to show you that we manage transmission and receptions of signal. The antenna was not strong enough to go above 70 gigahertz, so we only did it at 65. But those systems could work at higher frequencies. That's not the problem. And this is both a receiver and a transmitter. That's a transceiver on a chip. So where are we at? I think I've shown you that this is a valuable solution to do high data rate wireless transmission. And key to this progress has been the development of photonic solutions, because they offer us the versatility and the connection with the optical fiber. So we can go directly from an optical fiber networks into the terahertz wireless. There's a lot of solution coming up. Very interestingly, some CMOS, indium phosphide, and MMICs and RTDs based terahertz wireless progressing very quickly, which means that I can have quite good amplifiers system at higher frequencies that are working. Now there are some commercial amplifiers at 300 gigahertz that are excellent with quite low noise figure. We have way above 100 gigabits per second already from those signals. We have almost reached a terabits on some of those lengths. And a monolithically integrated receiver has been demonstrated, and it's only 300 milliwatts of power consumption. So there are still a few questions we need to answer. I said I didn't have all the answers. Am I right to try to make this transparent to an optical network? Maybe there are some better ways to do this. I still believe optics is more efficient, so I need to be as transparent as I can to try to make it work. Can I reduce the energy consumption? Because that's still a problem with radio. We are still looking at relatively short distances, and we still need to reduce the power per bit at those data rates, the energy per bits. Can I improve the transmitter power? That's one of the biggest problems we have, is that we have 10 microwatts from those transmitters. But amplifications mean more energy, so where do I go? All I have shown you was without amplification at the transmitter. And can we build emitters arrays and get efficient phase arrays to do beam steering, addressing mobile? This is a good question, and that's actually one of the big questions in the field at the moment, is nobody has a proper solution for any of this to date. Doesn't mean we won't, just to date. But I thank you very much for listening. I hope I'm on time. And I'm waiting for your questions.
Thank you very much. We have time for one quick question.
Yes.
So very interesting. Obviously, there's lots of applications. Can you do bidirectional transmission?
Duplex, you mean transceiver back and forwards, yeah?
Yeah. So can you have? Does it have to be physically separated by a certain amount if you wanted to have?
No, the biggest issue, it's feasible. So that last device I showed that had the two devices side by side on a chip.
Yeah.
It's feasible to do both ways. The biggest problem we have at the moment is basically on such a chip is the communication between the two of them. So you have to separate the frequency well enough to avoid crosstalk between the two. So the demonstration I showed, it was used one way and then the other way. But technically, the chip itself is connected to the same antenna, a single antenna, so they are not separated physically.
Okay.
So technically it's feasible. It's just a question of avoiding that crosstalk.